Hello, and welcome to this Earth Science lecture. Let's start at the beginning. So the Earth is about 4.55 billion years old, or 4,550 million years old. Pictured here are two different ways to visualize how old the Earth is and when different events happened. On the left, major events and stages are shown through a clock face. So here's the formation of the Earth about 4,550 million years ago, and as we go to the right, clockwise, we can see different stages of the Earth over geologic time. On the right is a time spiral. So here's the formation of the Earth here, and as we spiral up, skips a lot of the earlier stuff, and then we start to get into a lot of the evolutionary, like when life formed more, and we see a lot of the different evolutionary steps forward. But we're getting ahead of ourselves. So how did the Earth come to be in the first place? So this is a comic book storyboard that does a good job of showing how the Earth first formed. So first, a massive star exploded in a supernova, and it created a nebula, or a cloud of gases and dust in space. And it was enriched in some heavier elements like iron, because it was the remnant of a really big star. And then about 5 billion years ago, this cloud of gases and rock dust began to shrink and pull together under gravity. And as it shrank, it started to rotate and spin, and material towards the center compressed and grew hotter, and it created what we now know as our sun. And then around this sun swirled a bunch of different material. And then around this sun swirled a disk of material which grew white hot from the compressive forces, and then this disk of leftover material eventually became different planetary bodies, including the Earth. Thus the Earth was born, and for a long time the surface of the Earth was completely molten hot, and there was no solid surface of it. And at this time, when the Earth was still molten hot, it was struck by a planetary-sized object called Theia, and it was a glancing blow, and what it did was it flash melted the surface of the Earth, and it also blew off a big good chunk of the Earth that eventually became our moon. And so that's how we got our moon and our tilt. So the Earth was already spinning after formation, but this planetary-sized body that hit us and glanced and gave us a glancing blow, it formed our moon, and it also tilted the Earth, and that's very important because it's why we have seasons. So the layers of Earth formed about 4.5 billion years ago, because remember, even though the Earth is a little bit younger than 4.6 billion years ago, it was completely molten for a really long time. And so the Earth formed into these different layers. So we have an inner core, which is solid, an outer core, which is liquid, a mesosphere, which is solid, and then an asthenosphere and an upper mantle, and then our crust. And so that's an inner core, outer core, mantle, and then the mantle actually includes the mesosphere and the asthenosphere and the crust. These layers are separated based on density, with denser material towards the center. And the asthenosphere and the mantle are what make plate tectonics possible. So plate tectonics are why continents move on this planet. And so in certain areas, we have the formation of new crust, and then these plates move due to the asthenosphere. They float on the asthenosphere, and then they eventually hit converging plates, and one plate is subducted under another. And so over geologic history, the continents have actually been moving quite a bit. So this is what it looks like today, and in black you can see the boundaries of different plates. But at different periods in time, the continents have been moving around because of plate tectonics. And so at one point, all the continents were kind of one supercontinent called Pangaea, but they've actually been in many different orientations throughout the years. So let's get back to the history of the Earth, and we're going to look at it in the form of this clock face here. So first was the Hadean Eon. The Hadean Eon was like Hades. For a good chunk of the time, the Earth was molten, and then even after it had kind of solidified a bit, it was still pretty inhospitable, and so it was like a hellscape, and so that's how it got its name. It was a hot mix of gases and solids. It had almost no atmosphere. The surface was molten, but as Earth cooled, an atmosphere formed mainly from gases spewed from volcanoes. In addition to the heavy volcanic activity, there was also heavy bombardment by objects from space. So after the surface cooled, the water vapor that had been spewed out by volcanoes condensed and formed water. So volcanic activity actually gave us both our atmosphere and our water. During this time period, there's something called the faint young sun paradox. The sun, being younger billions of years ago, was actually fainter. It was only about 70% as intense as it is today. So the paradox is that with the young sun's output, the early Earth would have actually been expected to be completely frozen rather than this molten hellscape that we know it was. But we actually think that there was liquid water at this time after the volcanoes spewed out all this water vapor that condensed and became oceans and seas. So what's the cause of this? So the cause is actually the greenhouse effect. The greenhouse effect is something that still goes on today, and with it, shortwave radiation, such as solar radiation, it's visible light, passes through Earth's atmosphere, and then the solar radiation hits the planet and it's absorbed. It's then re-radiated back out as long wave radiation, which is infrared light. We can't see that. Long wavelength radiation is absorbed by greenhouse gases, and then it has the potential to be sent back down towards Earth, hitting it a second time, thus reheating it. So the sun emits shortwave radiation because it's hotter, while the Earth emits long wave radiation because it's cooler. And so because volcanoes had spewed out a bunch of greenhouse gases, of which water vapor is one, but many other greenhouse gases were spewed out by volcanoes too, the Earth's atmosphere was actually able to be warmer than what it should have been given just the sun's output. So our atmosphere and the greenhouse effect actually made liquid water possible. So the atmosphere contained greenhouse gases during the Hadean. And this is a look at how Earth's atmosphere has changed over time. This is what it looks like today. It's mostly nitrogen and oxygen, but back then we didn't have any oxygen yet, not much nitrogen, and we had a lot of ammonia and methane, and a lot of water vapor too. And water vapor and methane especially are really strong greenhouse gases. So next is the Archean eon. This was when life first evolved. Photosynthesis also evolved during this eon. So first we had life formed, and then photosynthesis. And photosynthesis was really important because it set the stage for oxygen to appear in our atmosphere. So with photosynthesis, you take carbon dioxide, water, and an organism can use light energy to convert that into organic matter, such as glucose, and oxygen. At this time, all life was unicellular. So even though we had life and photosynthesis evolved, it was all unicellular life. And before photosynthesis, microbes use CO2 and chemicals to produce organic matter. So here we are in the Archean, we start to see a lot of carbon dioxide, and that's really important for the formation of oxygen. And we're starting to see small amounts of oxygen down here, but not a lot, because it takes a long time for that oxygen to build up in the atmosphere. So next we have the Proterozoic eon. And during the Proterozoic, oxygen began to build up more in the atmosphere because photosynthesis had been around for a while, and we saw our first snowball Earth. So snowball Earth, the first one, happened about 2.3 billion years ago. So based on geologic deposit, it appears that there have been several Earth icehouse climates or events where all or nearly all of Earth's surface was covered by ice and snow, much more so than in recent ice ages. Possible causes are dust from the eruption of supervolcanoes, which actually reflects incoming solar radiation. Having the continents all clustered at the equator, remember plate tectonics, so continents could have been clustered at the equator, and oxygen being present in the atmosphere was also very important. These causes are not mutually exclusive and probably would have worked together to create this event. So let's go over these different causes. So first is dust from eruption by a supervolcano and the continents all being clustered at the equator. This actually increased the albedo of the Earth. So clouds, including particulates that are spewed out by a volcano, can actually reflect incoming solar radiation. And so the albedo is the amount of radiation that's reflected back. It doesn't get absorbed. And so ice has a really strong albedo, much more so than water, because water tends to have a darker surface, and so that solar radiation gets absorbed, whereas ice and snow are white, and so a lot of it just gets reflected back out. And then clouds can also reflect the sun out without absorbing that solar radiation. So dust from the eruption by a supervolcano, which would have put particulate matter in the atmosphere, which would have reflected the sun's incoming radiation, and the continents all being clustered at the equator would have reflected a lot of incoming solar radiation. So the continents at the equator really reflecting that light is because continents or landmass tends to have a higher albedo than water because it tends to be lighter. And the tropics at the equator get a lot more solar radiation. So if you're reflecting more of that tropical sun back out and not absorbing it, that's going to decrease the heat. The continents all clustered at the equator and oxygen being present in the atmosphere actually changed the chemistry of the atmosphere so that there were less greenhouse gases. The continents clustered at the equator led to the removal of CO2 because it rained so much at the equator that there was increased weathering, which added calcium ions to the ocean. Through something called carbonate chemistry, it actually pulls CO2 out of the atmosphere. Meanwhile, the oxygen in the atmosphere reacted with methane. Methane's a really potent greenhouse gas, and so oxygen reacting with methane and removing it from the atmosphere decreased the amount of a very strong greenhouse gas. So don't worry too much about the exact mechanisms here, but what you should remember is that having less greenhouse gases meant that more long-wave radiation could escape to space and not reheat the planet a second time. Remember that these factors likely contributed to Snowball Earth. So Snowball Earth was actually a positive feedback loop for itself. So because ice has a high albedo, more solar radiation was reflected by the ice and Earth's temperature further decreased, forming more ice. It's a loop that's a self-fulfilling prophecy. It's a positive feedback. And so we probably got out of the loop by a volcanic eruption that added a lot of new greenhouse gases to the atmosphere. So also in the Proterozoic eon, we saw eukaryotic life evolve. So we are eukaryotes. Eukaryote means it has a nucleus. But eukaryotic life was still unicellular for a long time. But then after eukaryotic life evolved, we then saw multicellular life evolve right there. And so that's when multicellular life really evolved. And in order for multicellular life to have evolved, we really needed to see a good amount of oxygen in the atmosphere because all multicellular life requires oxygen. And what you should note here is that the Earth has gone much longer without multicellular life in it than it has gone with multicellular life in it. And early multicellular life looks nothing like what you're thinking of. It doesn't look like you or me or a dog or a bird. It looked like this for a while. So now we get to the Paleozoic era. You may have noticed that we switched nomenclature there. So this clock has different units for different stages here. So these were eons, and now we're getting to eras. And I'll show you at the very end the divisions for geologic time, and we'll talk about that. But for right now, we're just going to focus on this clock. During the Paleozoic era, oxygen was much more prevalent in the atmosphere. There was also something called the Cambrian explosion, which is when there was an explosion of different forms of life. There's a lot of evolution because there were a lot of available niches, and life was able to evolve to fill those niches. For the first time, we actually saw vertebrate land animals during this time period as well. Fast forward to the Mesozoic era, life diversified even more, and we started to see giant reptiles, dinosaurs, and other giant organisms. Climate was generally much warmer during this era than it is today, though we are rapidly catching up. So here in red, you can see what climate was like then. The climate was like then. It was a fair amount higher than it is today. And here we are today, though these red dots are showing projected temperatures for 2050 and 2100 there. At the end of the Mesozoic era, between the Mesozoic and the Cenozoic, there was the Cretaceous Tertiary extinction event. This was when a giant asteroid hit the Earth and it caused a mass extinction event. This wasn't the first mass extinction. There have been several throughout Earth's history. Extinction events provide the opportunity for other organisms to diversify once the event that caused the mass extinction has abated. It takes a long time for the Earth system to become stable, and then for new species to reproduce and evolve. So after the asteroid that killed the dinosaurs, mammals were able to diversify. Then we go to the Cenozoic era. This was when mammals continued to diversify following that mass extinction event. And the first hominins, which are human ancestors, appeared approximately 2 million years ago. Some highlights from Earth's geologic history are that the only constant has really been change. Earth's climate has been warmer and colder than it is today. Earth's atmosphere was very different in the past and it continues to change today. Continents have been in vastly different locations and are still moving. Volcanic intensity has been really different, and the diversity of life has changed throughout all of this. So here's that geologic timescale that I promised you. You can see early on here we had the Hadean Eon, the Archean Eon, and the Proterozoic Eon, which are all ones that we talked about. This was also known as the Precambrian. And then we started to talk about different eras. We talked about the Paleozoic, the Mesozoic, and the Cenozoic. And these eras are also further divided up into different periods and so on. But we really just wanted to focus on talking about whatever stage helped us talk about the different events in Earth's history. And so that's why we broke it up the way we did and looked at the clock face the way we did. So we are currently in the Phanerozoic Eon, the Cenozoic era, the Quaternary period, and the Holocene epoch. The Holocene epoch started about 11,650 years ago and is the epoch during which humans came to dominate the planet. It has been proposed that the current epoch is actually the Anthropocene. This epoch would have started after humans industrialized. It's viewed as the stage during which human activity has been the dominant influence on the climate and environment. So there's been massive changes over geologic time. There's been massive changes to landscapes and the climate. But we're also in the midst of another mass extinction. The times in our geologic history when change happened this rapidly, there were actually huge, massive natural disasters, such as the asteroid that wiped out the dinosaurs. Today, we are the driving force for this mass extinction. So even though the only constant throughout Earth's geologic history has been change, we've only ever seen change this rapid with huge, massive, global, worldwide disasters. In the rest of the lectures, think about how much humans are impacting the Earth today, or even how recently we came on the scene, how long Earth survived without humans, and how much we are changing it today.